Okay, which you consider that in terms of angle adjustment is absolutely minute. Yeah. You're looking at less than 0.1 of a degree.
A fraction of a second of an arc.
Yeah. And what you get are these definitive. So this is a map of energy with respect to linear position. And what you'll get is very definitive sweet spots. And the reason for that is actually quite simple. The reason for that is that you have to consider that at the end of the day, let me have a look off. At the end of the day, why you're so angular sensitive, which is something a lot of people find really, really difficult to believe, is actually perfectly normal, because let's just bring it up. So you take 0, which is directly straight on. You end up with a perfect energy unit. So it's 0.0, blah blah blah. Right? But if you consider what you've got here, in that situation, you've got your magnet here, you've got your biased ferrite, and you're performing a rotation. But now you have to look at it from an applied field point of view. So the applied field of this to this is this. And if you had an unbiased magnet, what you would find is that your torque shape would go something like this, Okay, and you can just see the beginnings of this. If you ignore the bit in the middle here, Okay, so if you ignore the bit in the middle, you can see, well, I'm doing it the wrong way around. Let's go the right way around it, depending if it's repulsion or attraction.
A positive peak there.
So here would be the expected torque profile. Now what happens between here and here is quite unusual, because between here and here, what you're actually doing is saturating the magnet. In fact, you're pushing it down its MH curve.
Saturating the ferrite.
The ferrite is pre-saturated. Okay, so the ferrite sits here. Okay, as you apply this repulsive field, it's basically just up and down. Okay, this is moving,
pushing it back down.
Crosses 0, which is where you get these kind of weird shapes in between. Because other than that, now if you actually pull that away, you would revert back to this shape. But the reason you get perfect unity is because in this situation, if I take away the field and just look at the torque shape, okay, you have two completely different MH relationships. You've got one in the middle, okay, MH1, and on the other side will be MH2. Okay. In this case, MH2 is actually the saturated, because the ferrite's here, So this would be MH2, okay, and this is MH1.
Because you're going with the flow of the bias on the ferrite. So it's saturated on both ends.
It's saturated on both sides.
Sure.
Now, so when you do something where you've got perfect symmetry, you've got absolute perfect symmetry. Okay, the impacts of MH1 and MH2 is the same. So the change in torque here and here balance out. And then as you now apply an angle to it, what you're actually doing is you're changing the net change, if that makes any difference, if that makes any sense. So while your MH1 relationship will stay pretty much here, your MH2 will stay here and here, the torque that you're varying changes. So then if I just take, let's say, if I'm making any sense here at all.
No, we're doing okay. I'm hanging on the edge here, but it's okay.
So now here's exactly the same situation, okay, with respect to hang on a minute, sorry, that's the wrong spreadsheet. Let's go again, the right spreadsheet.
Let me just be clear, the purple line is...
Okay.
There.
So the blue line is torque, and the purple line is energy,
Fine.
And what you'll find here is now this looks identical. In fact, let me just go back. Okay. So if you just flip between, that's face on. And that's at the tiniest of angle. I mean, that's a second. Okay.
Right.
But in this situation, what you'll see is the torque graph shifts over ever so slightly. But also, what's happening is that you're having
push that way.
You're moving the applied area of the asymmetry. So all of a sudden, or the applied area of the MH. So all of a sudden, MH2 on either side of it doesn't have the same net effect.
No, it's not the same shape.
It's not the same shape. So you start to squeeze out these really, really tiny differentials. Yeah. And the problem is, from people who try to replicate this, okay, they're looking at first of all what are very small differentials, but what are absolutely completely minute angle changes. I mean, we're changing linearly here 0.05 of a millimeter, which in respect to this setup is a tiny amount. But the effects...
So that's altering this angle here as you move in.
No, what we're literally doing here is simply sliding this out in a linear fashion.
Yeah, so it changes the angle it subtends to at this.
Yeah, so basically we're moving this out in, say, 0.01 millimeters or whatever they are, okay? That has a net effect of actually angling this with respect to this.
Yeah,
and that's actually quite a safe way to go through this, but so if you look at a 10 millimeter change, it's really not a huge angular change, but this kind of way of testing it actually allows you to do minute angular changes and also to see how completely significant the impact of that is.
Yeah, sure.
And so angular sensitivity is just...
So you're dealing with systems with very narrow bandwidth here, and you can miss it so easily.
Yeah, and the point is to understand why that is, and the reason why that is simply that you're playing a game in the difference of the difference.
Yeah.
At the end of the day, So I mean, you're looking at the difference on one side to the other side, and because magnetic fields will decay at 1 over distance squared. 1 over distance squared can be a very significant.
You're moving a penny from one end of a 5-ton beam balance to the other.
Exactly. Yeah. So that's a pretty handy rule.